Hi everyone. Welcome to the second half of Chapter 13, Bivariate Regression Analysis. So we're right here on about lecture slide number 21, and we will be finishing it all the way through lecture slide number 60 or so. But here on this first one, I've put the data easily copy and pasteable into Minitab, so that if you'd like to follow along as we go, you can do that as well. Just put copy paste into Minitab, and then as we go you can do, say, stat reg, fit reg model, stuff like that. Okay, so that's some of the menu things that we're going to be doing today. All right. So our new topic is bivariate regression. We just finished up correlation. So regression analysis is a little different than correlation. Correlation analysis tests for the strength and direction of the relationship between two quantitative variables. So that always tests for it's a strong correlation, weak correlation, and then we also know whether it's a positive or negative correlation. Regression analysis is a little bit different because we're going to have some data here, and we are going to fit the regression line right smack in the data to minimize the sum of squared errors. So we're going to minimize the distance. We're going to choose both A and B, right? We're going to be choosing the slope and the y-intercept in order to get it as close to these data points as possible. And that will be fitting our regression line. We're going to have Minitab actually do it. Usually we use ordinary least squares, and we'll be talking more about ordinary least squares regression later. But so we are going to fit this regression line, and we get a lot of really interesting and useful information. You can see how you could choose different slopes, different y-intercept terms in order to get as close to these data as possible. And we'll be using the least squares principle for the best fit. The two most important pieces of information that we get from a regression are as follows. These are the two most important things that we get from regression. We get the relationship between x and y. It's just not whether it's positive or negative, but we actually get if my calls go up, how much will my sales increase? And that is your beta, or your slope, the rise over the run. So for each additional sales call, how much will sales increase? And that's going to be your beta, and it's going to give businesses a lot of really important information. For instance, if we can get brokers to make one additional call and sales go up by thousands of dollars, well, we may want to implement a program in order to increase sales calls. Kind of makes sense? So this is a really important piece of information. It's beta. We're going to spend a lot of time and energy trying to understand the relationship between x and y, which can be best summarized as beta. Beta tells us for each additional unit of x, how much does y increase. The second piece of information is we can get predicted y. We can use this regression line, assuming that this is the true relationship between x and y, and we can get a predicted value. That is, well, what if we make 100 calls? Well, if we make 100 calls, this regression line predicts that we would have this many sales. Does that kind of make sense? This is graphically a way to understand predicted y. Graphically. So those are the two most important pieces of information. We're going to focus on them again and again throughout the rest of this chapter. All right, so let's talk about B, which is your beta. So remember that it is the slope, the rise over the run is your beta, right? The rise over your run is your beta. So in order to interpret how to interpret the slope, we would say for each additional unit of x, y increases or decreases by beta times the units of y. We have to use pretty much this exact language, so you should memorize this early and often. For each additional unit of x, y increases or decreases by beta times the units of y. So here we have number of cigarettes smoked, cigs, number of cigarettes smoked per day. Right? How many are in a pack? It's either 10 or 20 in a pack. I'm not sure. But anyway, so here we have cigarettes smoked per day, and then we have lung cancer mortality per 100,000. So as cigarettes smoked go up, what happens to mortality? Deaths go up. And the slope is 11.26. So we would say for each additional cigarette smoked, deaths increase by 11.2 per 100,000 a year. Does everybody see how we use this particular verbiage in order to interpret my B? Let's try this one more time. Here we have driver age and then sign legibility distance. How at age, say, 25, you can read the sign when it's 500 feet away. But at age 65, you can only read it when it's 350 feet away. So as age goes up, it's harder to read. Shorter and shorter distances in order to be able to read that sign. So that's a negative relationship. As driver age goes up, distance goes down. And that's why we have this negative here, right? So as age goes up, distance goes down, doesn't it? Yeah, it goes down. So as age goes up by 1 year for each additional unit of x, as age goes up by 1 year, sign legibility distance goes down by 10.1 feet. Does everybody see how to interpret this B and the relationship between age and distance, or the relationship between cigarette smoking and deaths? Right. Check. All right, so our regression analysis, we've got these variables, and the regression equation is going to be y is equal to a plus bx. I know a lot of you guys learned it as y is equal to mx plus b. But for some reason, in regression and economics, we're sticking with this. Y is equal to a plus bx. So here's my y-intercept term. Here's your slope. And so this x is my independent variable, and y is my dependent variable. My dependent variable is y, and that'll be my response. Y is my response, and it's responding to changes in x. Y is a response, and it's going to respond when we change x. So x is a predictor variable. So let's take a look and see if we could figure out which is our x and which is our y. It says we have data, and our data are on size of the home, measured in square feet, and cost to heat that home in January. So is cost to heat the x, or is cost to heat the y? We should kind of think it through as x affects y. Y will respond. So when we change x, y will respond. So this is pretty obvious then. The size of the home, as we change the size of the home, cost to heat the home will respond. X, size of the home, affects the cost. Yay, size of the home, x affects the heating cost. Likewise, car weight, the weight of the car will be your x, and as we change the weight of the car, the miles per gallon will respond. So that's why we have x affects y. And so you've got to be able to figure that out in order to put the data in correctly into Minitab. So let's take a look and see if we can figure out how to do heating cost. All right, I happen to have already put heating cost and home size into my mini tab here. So I've got 15 observations of the cost to heat a home in January, and then the different sizes in thousands of square feet. So 2.0, is that a 2 square foot home? No, it's a 2,000 square foot home, right? Because home size is in thousands. So 2.0 would be 2,000. How much would 1.0 be? A 1,000. 1,300, 1,500 square foot home, and then the cost to heat it. So let's run a regression. To run a regression, we are going to go stat, reg, reg. Stat, reg, reg, and then we are going to go here to fit regression model. One more time. We're going to be going to stat, reg, reg, fit regression model. And my response variable will be heating cost, and then my continuous predictor will be home size in thousands. So X, home size, affects Y, the cost to heat it. And then we're just going to say OK. And out will pop this output in the session window. So here's my regression equation. This is the coefficient, so we can have my coefficient, a t computed, and a p-value for that coefficient. We'll be looking at this important metric, which is the coefficient of determination. And then later we'll be using this analysis of variance table. But you can see the model summary. It shows my y, my intercept, the slope, and my x. All right. So this kind of shows us just putting it in there. We'll do predict later. So now let's write the equation and graph it in cost and home size space. So we want to use this equation right here, but graph it. So I see my y-intercept, I see my slope, I see my blah, 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 right? So let's take a look at that. So here would be cost on the y-axis. Here would be square footage in thousands on the x-axis. I would say my y-intercept is a -2, so I had to make that cost a -2. And then this is the slope. My slope is 1.52. So now, can we get a predicted heating cost for a home with 2,000 square feet? Well, if we have 2,000 square feet, we're going to put this 2 into this regression equation and get a predicted value. So when x is equal to 2, my predicted cost hat, my cost hat is the predicted cost off the regression equation. My predicted cost, when it's a 2,000 square foot home, is that you're going to have the monthly heating cost at $303. That's a whopping heating cost. It's obviously not for Jacksonville. So this is kind of what I wanted you to get. I wanted you to be able to put the data in, get the output, and then graph it, showing your y-intercept, showing your slope, showing where a point on this line would be for a predicted heating cost. So that's the first thing that we need to do. Here's a bunch of equations. I am not going to test you very much on equations. I just don't think that they're horribly interesting or useful. Statisticians need to know them, but we need to know how to interpret them. All right. Again, most important, what does B mean? So if we do run copiers sold, this is number of sales calls, and this is a number of copiers sold. For each additional sales call, number sold increases by 0.26 copiers. Or you can multiply each by 10 because it's a linear relationship. So you could say for each additional 10 sales calls, number sold increases by 2.6. And then again, what's a predicted number sold? All right, let's take a look at that. That's kind of what we're doing right now. All right, calls and sales, we can do that pretty easily. This is my output. We did this already. We're doing it again. For slope, y-intercept, a y-hat. When calls are equal to 50, your y-hat is 32. So here's the equation for it. Basically, it's not patently obvious that this is the equation and that this equation is reflected in this graph. That's what I want you to make the relationship. I want you to make that transition from a mathematical equation into a graphical analysis. Let's try and do this again, because this is kind of interesting. So far, we do know which is a predictor and which is the response. We know how to put it into Minitab and get that output. We know how to summarize in words what B means, but here I want to play with some units, because the units are what's really important. Here, for each additional unit of x, well, if x is in tens, then you would say for each additional 10 units of x. And then here, the unit of y, we have to multiply beta times the units of y. And if the units of y are in thousands, then that has to be $1,000 or 1,000 units of whatever it is. So don't drop the units. All right, here we have, for example, number of competitors in the region, and that affects the company's revenues. As a number of competitors in the region goes up, what happens to revenues? They go down, don't they? Revenues go down. All right, so let's interpret B. For each additional competitor, each additional unit of x, revenue decreases, that's a negative, decreases by 1.9 times $1,000 because revenue isn't $1,000. 1.9 times $1,000 would be $1,900. Does everybody see how we applied this particular equation to this example with the units? For each additional competitor in the region, revenue declines by $1,900, not $1.9, $1,900. Here we have number of employees and human resources costs. Number of employees are in hundreds, and we think that affects the costs, HR costs. So, for each additional 100 employees, HR costs go up by $1,690. Everybody see how we got $1,690? Because the units of Y are in thousands of dollars. All right, here we have price of used cars in hundreds and mileage in thousands. For each additional 1,000 miles on a car, price of the used car goes down by $280. Does everybody see how it's 0.28 times 100 would be 280? So you definitely need to practice some of these, but it's pretty darn straightforward if you do practice. Multiple choice questions, I'll let you take a look at those. Let's see. Here is starting salary and intern hours in tens. Regression equation is starting salary is equal to 55.4 plus 0.013 intern hours 10. That looks like it's true to me. What's the y-intercept? This is the y-intercept. What does a beta mean in words? For each additional 10 hours of internship, starting salary goes up by $130. So B. Does that make sense, you guys? I don't think we've interpreted this yet, but you can come back to that. All right, so let's do a test for whether or not the relationship between X and Y doesn't exist. Either there is a relationship, so that as X goes up, Y goes up, or there's not a relationship. There's not enough evidence to suggest that there's a relationship. Calls could be high, calls could be low, and sales still are not affected. So what we're looking at is we're looking at what would it mean if your beta were equal to 0. It would mean calls do not affect sales. The alternative hypothesis, very important hypothesis for this second half of the chapter, is beta doesn't equal to 0. If beta does not equal to 0, then when calls go up, sales go up a lot. Or they may go down. Who knows, whether it's a positive or a negative. But if your beta does not equal to 0, then there is a relationship between calls and sales. Calls do affect sales. So this is going to be the underlying hypothesis that we're going to be testing. Beta equal to 0, beta does not equal to 0. Statisticians, again, tell us exactly what we can be tested. They tell us that it's going to be a t distribution, that this test statistic is following. They're going to create the test statistic for us, and then we'll think for ourselves, just like we did last time, and get our statistical conclusion. So these are the same 5 things that we have to know about hypothesis tests. This is just one more new hypothesis test. All right, so this is how we're going to use the output. Let's go ahead and just run it just for fun. We'll get calls and sales and run it. I'm going to go back here to my 21, put in calls and sales. I thought I had done it already. Maybe I did. Oh, I bet I did. But calls and sales are already in here. All right, calls and sales are already in here, so I'm going to run it. Stat, reg, fit regression model. Stat, reg, fit regression model. And my response, we think that if we make more sales calls, we're going to have more sales. If we make more sales calls, we're going to have more sales. So what's my response? Sales and calls is my continuous predictor. So calls affect sales. And here is the output that I get. Calls and sales. Sales are in thousands, I believe. Oh, no, sales are numbers. Those are numbers of copiers sold. All right. All right, here is the output that we just got in Minitab. So my hypothesis would be beta is equal to 0. X does not affect Y. Number of calls does not affect sales. Number of calls does affect sales. My T computed. My T computed is going to be on this. Remember, I always have a computed test statistic, and then right next door is a p-value. Pretty much always that happens. So this is coefficient 0.26 divided by 0.04, the standard error, and that is 6.21. So there's my p-value. So this is an equation that I will be asking you. So make sure you know that equation. This divided by this is going to be equal to this. And basically what that means is that for the sample is that our beta is 6.21 standard deviations away from 0. That's a lot of standard deviations away from 0. So probably we'll reject and conclude that calls do affect sales because that beta is really far away from 0. The t-table. This we get from a stat textbook. Statisticians are really smart, and they have told us that our degrees of freedom are t alpha over 2 n minus k minus 1. Again, this t distribution depends upon the sample size, so that's why we have these degrees of freedom. And then t 1 minus alpha over 2 n minus k minus 1. So that turns out to be, n is my sample size, and k is the number of predictor variables. Right now we just have calls. Pretty soon we'll be adding more predictor variables to explain the variation and why, but for right now we just have calls. We just use calls to explain how many copiers are sold. So this is going to be alpha over 2, 0.05 divided by 2 is going to be equal to t.025. Alpha divided by 2. N minus k minus 1 will be 13. N is 15, minus k minus 1 would be 13. The degrees of freedom that we use in this, we can grab right off the analysis of variance table. The error. Analysis of variance error. So, what are my table values? T02513, T97513. T02513, T975. We have a p-value right here. P-value less than alpha, reject. X does affect Y. Reject H0, conclude HA is true. Number of calls does affect sales. Reject H0, small p-value. Let me show you about these t-table values and how to look those up. You don't have to, because why? Why don't we have to look those up? Don't we have to compare it to t computed and t? No, we use a p-value, right? P-value versus alpha. But let me just show you how to look this up in case you wanted to. All right, so what we bring to the table with the t distribution, in case you don't remember, is that it's symmetric around 0. So what we're going to be looking up is t.025. We're going to be looking up t.025 with 13 degrees of freedom, and that's going to be equal to 2.16. Does everybody see how that's 2.16? 025, t.025 down to 13, ding, 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 2.16. All right. Shrink this, baby. 2.16. Where am I? Darn it. Sorry, you guys. All right. So, t.025 with 13 degrees of freedom is going to be equal to positive 2.16. And it turns out that T975 is going to be negative 2.16. So what you're going to be doing is you're going to be comparing this to these two. A positive 2 and a negative 2. We got a positive 2 when we looked it up in Google, and we know we just put a negative sign on it to be the other bound. Negative sign on it. So that's going to be positive 2.16, that's going to be negative 2.16. And what we're doing is if the rejection region is if this number is greater than positive 2 or smaller than negative 2, then you'll reject, and sure enough it is. It's greater than positive 2. P-value is less than alpha, just use a p-value. All right, so there's our hypothesis test, and this is really all we need for the hypothesis test. Number of calls does not affect sales. Number of calls does affect sales. My t computed off of the Minitab output. The t table value, 025 and 975 with 13 degrees of freedom, n minus k minus 1. That is always going to be n minus k minus 1. My p-value right off here. Right next to the t is always its own p-value. It's on the same row. That's how we got that 0. And p-value less than alpha, reject. All right, so now how are we going to summarize what the relationship is between calls and sales? For this, anytime we use a summary, we must look at the p-values. We must look up the p-values because we are interpreting it not for the sample, but for the population as a whole. The population as a whole. So if my p-value is greater than alpha, we do know my statistical conclusion would be there's not enough evidence to suggest that HA is true. There's not enough evidence to suggest that calls affect sales. If my p-value is greater than alpha, for the true population, there's not enough evidence to suggest that calls affect sales. So my recommendation is don't implement a program to increase calls, dude, right? That's not what you want to do. On the other hand, I would have a different summary and different recommendations if I found there was a true relationship in the population as a whole. If I found there was a true relationship in the population as a whole, then I would know that for each additional call, copier sales increase by 0.26 units. So we use the slope. The summary is just like the slope. For each additional unit of X, Y increases or decreases by beta times the units of Y. For each additional call made, copier sales increase by 0.26 units. Recommendations: do implement a program to increase calls in order to increase copier sales. So your entire programs change depending upon statistics. Your entire programs change depending upon statistics. Your recommendations, your informed choices are totally different, and it depends upon the p-value. What is happening in that population? Not in this sample, in the population. All right, so here we have another example. These are, again, just more examples so that you can follow along and gain a ton of confidence and really know what you're doing. So here we're going to put these data into Minitab. I've got bidders, and this is the million. So this is the price that the project gets, and this is the number of competitive bidders in the process for very similar, for bunches of different bunches of very similar projects. These are the number of bidders that are submitting bids, and this is the final project price in millions. So we're going to go stat, reg, fit regression model for bidders in millions. So do you think that the number of bidders affects the project price, or do you think that the project price affects the bidders? They're all very similar projects. All right, I'm going to say that the bidders affects the price. The price doesn't affect the number of bidders because they're all very similar projects. So then we say okay, and out pops my regression equation. And notice we have my coefficient is negative. As bidders goes up, project price goes down, and I have a p-value less than alpha here. So the first thing is they want you to, we need to fit the regression model and then test the hypothesis, beta equal to 0. My beta is equal to 0 would be number of bidders does not affect price. Beta not equal to 0, number of bidders does affect the price. There is a relationship between price and the number of bidders. I get my T computed off of Minitab right here. T computed. T table 025 and 975 with 13 degrees of freedom right here. My p-value is right here. We're going to use this one up for bidders. That's the p-value we're looking at because that's your beta is equal to 0, beta not equal to 0. That's my p-value. Reject, number of bidders does affect price. My summary, Because my p-value is less than alpha, I use the slope. I don't say there's not enough evidence. I use the slope. For each additional bidder, project price is reduced by $0.467 million. Use resources to bring more bidders to each project. Oh yeah, we were able to find a statistically significant relationship. And this, by the way, is really true. I'm also a public finance economist, and I will tell you the one way to reduce corruption, reduce spending, etc., is to increase the number of competitive bidders. All right, so here are some questions with answers, but do the questions first. Don't just look at the answers. Do the questions first and then make your mistakes. All right, new topic. All right, so far what we've done is we've put data into Minitab, we've gotten regression output, we've interpreted coefficients, given summaries and recommendations based upon hypothesis tests of beta equal to 0. Now we're going to go a new topic, which is very important. It's called the coefficient of determination. And it kind of informs us as to the quality of the regression. How well do the data fit the regression line? How strongly is there that association between X and Y? So we are going to calculate, actually Minitab calculates your R squared. Notice we have right here R squared. So as a part of every output, we have a model summary and we've got an R squared right here. I just wanted to show you that it exists. Okay, R squared ranges from 0 to 1, or in Minitab, it's usually reported in percents, so it goes between 0 and 100. R squared, it's the square of the Pearson correlation coefficient. The first part of chapter 13, we learned about the Pearson correlation coefficient. Well, that Pearson correlation coefficient squared is going to be equal to the coefficient of determination. R squared shows how tightly the data fit the regression line. As R squared increases, data fit the regression line more and more closely. You can see here, R squared would be close to 0.9. Here, 0.5, and here, 0.1. Very scattered. This is a lot less scattered. Regressions with a high R squared, those that are close to 1, usually have small prediction intervals and very accurate predictions. We'll be talking about prediction intervals and things of that nature, but we can predict quite accurately when we have a really high R squared close to 1, because then we have good ideas about the variability of Y with respect to X. And then R squared, the interpretation. It is percent of variation in Y that is explained by X, variables in the regression. The percent of variation in Y that is explained by your regression equation. So for instance, right here, again, we have the R squared. 74.8% of the variation in the number of copiers sold is explained or accounted for by the regression equation, by the variation in the number of sales calls. So my X variables that I've chosen have explained a lot of the variation of why sales are high and sales are low. Another example, here we have bidders. This is the one with the bidders and the price. And we have an R squared of 49. So interpret R squared, 49.9% of the variation in net project price is accounted for by the regression equation, or the number of bidders. So this is a very important kind of summary statistic that we always look at. Is your R squared really high or is it low? Was your X a good predictor or not so much? Was your X a good explainer of why your Y variable goes high and low or not so much? We look at this, the coefficient of determination, R squared. All right, we did predict sales. You guys remember that. We put 50 in the regression equation, and so then we get a point on the regression line because this y hat is the regression line. Remember, y is equal to a plus bx. Here's the line. Those are individual data points. And we can look at that and actually find the point for the predicted. But so now what we want to address is a question of, will everyone who makes 50 calls sell 32.98 copiers? Will every broker or every salesperson who makes 50 calls sell exactly 32 copiers? Probably not. Statisticians rock. They know exactly, they don't know exactly the number, but they can tell you with 95% confident limits how much those guys will sell. If you took a good sample that is representative of the population, you have so much information. It's unbelievable. So what statisticians know is that for each value of X, so here's calls, right? For each, as the number of calls increase here, sales will also increase, but it's going to be a probability distribution. So not every salesman who makes 50 calls will make exactly 32 sales. Some will sell more and some will sell less. But this is what rocks, is statisticians know that there's going to be a normal distribution around predicted sales. So for every unit of X, there's going to be a probability distribution of sales. Some guys are going to sell more, some guys are going to sell less. And then statisticians can give us a ton of information. Statisticians know what to do with a normal distribution. They really do. And so basically what we can do is you're going to kind of figuratively see this probability distribution. But we're going to get two limits. Statisticians can give us the 95% confidence interval, and then they can give us the 95% prediction interval for any given level of X. We're going to get a 95% confidence interval, and that will be 95 out of 100 times when a group of salesmen makes 50 calls, then their average will be between these limits. The average of all the group that made 50 will be between these limits, and it tends to be pretty darn accurate because we are great at predicting averages for a group. We're not so good at predicting individuals, but we're really good at predicting averages, which is why you have to pool insurance. You can't just insure a single individual. That may be a cancer survivor guy, right? You can though predict very well the average for the group. And we rely on that a lot for our stock portfolios, for insurance portfolios, pooling risk, things of that nature. We're always going to want to know accurately the average, and that's our confidence interval. The prediction interval is, we can be 95 out of 100 times we'll know the range where a single individual sales will be. And that's going to be much wider because an individual has much wider variability. The average, much smaller. Note that confidence intervals are wider when X is far away from the center. So if this is X bar, that's where my narrowest prediction interval and confidence interval is. As we get further and further away from the sample, these really spread out quite a bit. So we have 95% confidence intervals and 95% prediction intervals. The confidence interval is for the average of the group. Prediction is for a single individual. So we will be checking the underlying assumptions. Just don't you worry, we will be doing that. But for right now, let's just assume these assumptions underlying the linear regression. For each value of X, there's Y values that are normally distributed. The standard deviations are roughly equal. And the Y values are statistically independent. So one Y doesn't depend upon the previous Ys. So computing interval estimates. A confidence interval reports 95% confidence limits for the mean. Prediction interval reports 95% limits for individual values. The confidence and prediction intervals are narrower when r squared is closer to 1. So when you have a really high r squared, the data fit the line really well, you're going to have a narrow confidence interval. Prediction is most accurate and intervals are most narrow around x bar, the average value of x in your sample. And you should never use a regression to predict outside the sample range. You can't say, well, wow, 20 calls worked great. Let's do 2,000 a day. No, that's not going to work, okay? You can't extrapolate outside the sample range. And the reason is because regression is not a crystal ball. It does a great job of predicting for the sample range, but outside of that, it doesn't do very well. So here we have formulas again. Not terribly interested in formulas. No. Now, let's let Minitab do that. You know, I used to do it, and it just didn't do me any good to just divide 1 by n and then add it to the sum of x minus x bar after calculating it for 3 hours. Let's let Minitab do it. So we get predicted sales and confidence intervals, 95 out of 100 times, blah, blah, blah. Let's take a look at this confidence range. I would rather look at Minitab output, personally. It's a prediction interval. All right. We've got sales calls, and we want to predict what will sales be when calls are 50. So let's show you how to do that in Minitab. In Minitab, we're going to use these data on calls and sales. Stat, reg, reg. We have to first, fit the model, and then the second regression we can predict. But first, we have to fit the regression model. We're going to have sales and calls. So we run the regression, and now we can predict. Stat, reg, reg, predict. So now we're going to be predicting y for a particular value of x. So my calls, I'm just going to put in 50. If calls were in tens, then I would put in 5, but calls are just calls. So here, my fitted value, there's my y hat, and here's my 95% confidence interval, and here's my 95% prediction interval. So which one is wider again? An individual. Trying to predict for an individual is a lot more variable than predicting for a group of brokers who make 50 calls. The group of brokers that make 50 calls would have sales between here. Any single individual, 95 out of 100 times, it would be between these levels. So, stat, reg, reg, predict, response, sales, calls, 50, okay. Interpret predicted sales, interpret confidence interval, interpret prediction interval. These are the very typical questions that you can expect. So, when salespeople make 50 calls, predicted sales are 33 units per month. So you see, that's your fit. Under fit is your y hat. Fit is your y hat. A point on the line. That is a point on the regression line. Interpret confidence interval. When a group of salespeople make 50 calls, 95 out of 100 times, the mean sales for the group will be between 27 and 38 units. Prediction interval. For an individual salesperson who makes 50 calls, 95 out of 100 times, the mean sales for the group. For the individual will be between 17 and 48. The sales for the individual, not the mean. So we have confidence intervals, prediction intervals. We can get this plot, stat regression fitted line plot, and that's pretty easy. All right, so here we have a regression skills check. We have processor speed and laptop price. We have the price of a laptop and then how many gigahertz they have available. So we are going to put these data into Minitab. We will test beta is equal to 0. We will predict when your speed is equal to 1.8 gigahertz. You will interpret the prediction interval, the coefficient on processor speed, so that's your beta, and answer the question, is a prediction interval around y hat larger or smaller than a confidence interval in y? So when we put these data into Minitab, we run the regression, and this is my output. Beta is equal to 0. X does not affect y. Processor speed does not affect computer price. If beta doesn't equal to 0, X does affect y. Processor speed does affect computer price. We've got my T computed, my T table, p-value reject. Processor speed does affect computer price. We get a fitted value, stat reg reg, and then predict speed is equal to 1.8. When processor speed is 1.8, predicted price is 880. Prediction interval, 95 out of 100 times when the computer has 1.8 gigahertz, price will be between 502 and 1258 right here, prediction interval. Interpret coefficient on speed. For each additional gigahertz, computer price increases by $704. Here's my beta. Confidence interval is narrower because it's much easier to predict an average than an individual observation. And here's a bunch of questions, true falsies. Here's the data that you'll be using for it. And then there's the answers with some explanations. So hopefully this really helps. Homework 2 in this chapter is what's a dependent versus independent variable? How does the equation relate to the graphical representation? Can you do a hypothesis test? Beta equals 0, beta not equal to 0, T computed, T table, statistical conclusion. Can you do summary and recommendations? Don't forget to use the p-value. Summary and recommendations really differ depending upon the p-value because you're summarizing for the total population. We learned how to interpret R squared and kind of what that meant, a high R squared versus a low R squared. And then we interpreted prediction and confidence intervals. Probably the thing that gets students most confused is the units. So pay attention to that units. For each additional unit of x, y increases, decreases by beta times the units of y. So do not overlook that. That's very important. Anyway, we will see you soon.